sun. Therefore, the force exerted by the moon at point A is much greater than the force at B, whereas the force exerted at A by the sun is not much different from the force exerted at B. It's the difference in the force, the difference, not the absolute value. Does that make sense? So the difference in those forces is stretching the Earth much more due to the moon's presence than it is due to the sun. Make sense? Yes?
It's the whole Earth, including the North Pole and South Pole.
Everything. The whole ball of wax. So the difference in gravitational force between A and B is much greater for the moon's attraction than it is for the sun, as the diameter of the Earth is a much greater percentage of the distance to the moon than it is of the distance to the sun. And here you can see the values of those fractions. 8,000 is about 3% of the distance to the moon. But it's 8 or maybe 9 ten-thousandths of a percent, 9 thousandths of a percent to the distance to the sun. And just in case you don't believe my slide, here's somebody else's. So the moon's force on the far side is much less than at the center compared to the difference in the sun's force on the near and far side. The sun doesn't exert much difference. Now, the sun's force on the Earth is about 175 times as great as the moon's force on the Earth. So it's got to be the difference in the gravitational force that is causing the tides. Make sense? The actual tidal influence of the sun is about 44% of the tidal influence of the moon. Questions on that? Now you know the rest of the story, as Paul Harvey would say. So the moon governs the tides. The Earth, soil, rock, water, is stretched most by the moon when it's aligned with the sun, new moon or full moon. So now we're going to take a look at earthquakes. And there's a picture of a rift in the Earth at one of the fault lines as Los Angeles slowly separates from the rest of California and drifts northward to become a suburb of, heaven forbid, San Francisco. Afraid not, afraid not. Not even the boat traffic. I did a little research, okay? Every geologist that you talk to will say the moon does not affect earthquakes. You can't predict earthquakes based on the phase of the moon. I said, well, that's probably true. I mean, I've done a lot of research on this. I said, but what about the strength of the earthquake? Nobody has ever looked at the effect of the moon's phase on the strength of the earthquake. Because when the moon is new or full, the Earth is being stretched a little bit more than when it's first or third quarter. So the distance in time from new or full moon should be related to the strength of the earthquake. So here I took, let's see, 34, 44, 50, 58 earthquakes that occurred in California, okay, that had a strength of greater than 5 on the Richter scale. And I said, if the earthquake occurred at new or full moon, it would be here. And the further it got from new or full moon, the less the number of earthquakes at that strength. Amazing. So because the Earth is being stressed much more and stretched much more at new or full moon, the chances of a very significant earthquake are greater, even though the chances of an earthquake don't seem to be related. Well, I sent this to the Nobel Committee, and I'm expecting to hear any day. Is that Oslo? Maybe that's Oslo calling now. No. Interesting. Very interesting.
It's the earthquake of the entire Earth. The earthquake of the entire Earth.
Yes.
It also affects the North Pole and South Pole earthquake.
But he hasn't proved it yet.
Oh, here's the proof.
There's my proof. How can you say
That's
that?
what he said.
You've only looked at California earthquakes.
Yes, I only looked at California. So I called my friend in California once during an earthquake. You know what I said? And I greeted him. What's shaking? He didn't like that for some reason. I haven't spoken to him lately.
Did you just look at a certain, you said
58 earthquakes.
59, it says you remember.
Oh, 59. Okay, I miscounted.
A major earthquake, so was that
Yeah.
on the Richter scale
Yeah, yeah.
above a certain?
Above 5.
Above 5?
Yeah, because they get a lot of little tremors. And I've been out there during a little tremor, and I thought the earth was going to swallow me up. And they said, don't worry about that. That's nothing. Now let's talk about the double planet idea. I've drawn here a picture. Don't criticize my artwork, please. Of a barbell. Visualize a barbell with one light weight on one end and a heavier weight on the other. Okay? If you tried to find the balancing point for that barbell, it's possible that the balancing point would be right here. Right? And if you twirled it around that balancing point, the larger weight would go around in a small circle, depicted here by this, and the smaller weight would go around in a much larger circle, right? Can you visualize that? Twirling the barbell, okay? This is very similar to what's happening with the Earth and the Moon. There are 3 main reasons why astronomers believe that we are living on a double planet. First of all, if you look at the mass of the Moon compared to the mass of the Earth, and then look at that ratio for other planets and moons in our solar system, the Moon is huge compared to the Earth. It's a much greater fraction of the mass of the Earth than any other natural satellite is to its planet in our solar system. It's huge. Secondly, the Moon has an orbit that is always concave relative to the Sun. I'm going to demonstrate this with a video. And it's the only satellite that has such an orbit in our solar system. And there's a reference there. And if any of you want these slides, you can give me your email address after the lecture. I'll send them to you. And finally, as we've already pointed out, the sun exerts more force on the moon than the Earth does. So these three reasons. So let's look at the moons of the solar system. The ratio of the mass of the moon to the mass of the Earth puts the moon at about 1.2% of the Earth's mass. Not very much, right? But if you look at the numbers for other satellites, for example, the largest satellite in the solar system is Ganymede. It's bigger than the planet Mercury. But it's going around Jupiter. And Jupiter has about 99% of the mass of all the planets in the solar system. So the ratio of Ganymede to Jupiter is down around 7 10,000s, 8 10,000s. Much, much smaller in relation to its planet than our moon is in relation to our planet. And none of these other numbers are anywhere near that except for Charon going around Pluto, and we don't have to worry about Pluto anymore because it's not a planet. Forget that. Not going to let that disprove my theory. Very interesting, okay? The moon is huge compared to the Earth. The moon, by the way, was formed by a Mars-sized object that struck the Earth about 3.5 billion years ago and spewed material away from the Earth. Most of it was fluid. It was very hot. And it went into orbit around the Earth. And then gradually, the gravitational forces between those drops of molten rock and eventually cooled rock attracted each other, and they began to form the moon. We don't have any idea where it hit the Earth because it happened so long ago, and the Earth itself was so devastated by it, and everything became very hot and molten. So wherever it hit, it kind of healed over right away. And if you're thinking, well, why did he leave out Mars? Because Mars moons are pebbles. They are apparently captured asteroids. There's only 2 of them, and they're so small that they don't even have enough gravity to form a spherical object. They're very irregularly shaped. They're like pebbles you would find on the ground. Furthermore, they're about 100 billion times as small as Mars itself in terms of mass. I mean, they're nothing. One of them is going to crash into Mars, and the other one is probably going to leave Mars eventually for other parts of the solar system. And now we got to look at the orbital shape of our moon. This is what the orbit of our moon looks like. Remember, I said it was always concave relative to the sun. It never makes a loop. It never goes convex like this. It's always concave like this. It's always playing catch up because the Earth is moving around the sun. So the moon comes around and says, whoop, it went over there, whoop, it went over there, whoop, it went over there. It keeps moving. Did you get that, Mark? Told you I'd move around a lot. Can you see that? You see, the moon is constantly playing catch up, trying to catch up with the Earth. So like the barbell, the moon is not going around the Earth. The Earth and moon are going around the center of gravity of the system. Visualize that barbell, okay? That's what you're seeing. So the moon's path is always concave relative to the sun. Therefore, it's in orbit around the sun. Well, if it's in orbit around the sun, it's got to be a planet, right? Well, it's so small. Forget Pluto. Forget what I said about Pluto. The moon is going around the sun, not the Earth. The Earth-Moon system is going around the sun. We are on a double planet. Okay? Everybody convinced? This is what the path of the moon would be like if it went around the Earth. It would loop. And at times, it would be convex. It would curve away from the sun. But it never does. Or toward the sun, however you want to look at it. It would go like this. At this part of the orbit, it would be doing this kind of motion, which would make it appear to move backward in the sky. And it never does. It never does. All the other moons in the solar system do that. They all do that, except our moon. It's the only one that plays catch-up.
How does that affect us? The fact that it doesn't do that.
Well, it tells us that it's additional evidence for the fact that the moon came from the Earth. We were not captured. The moon was not captured like the 67 moons of Jupiter. 67 moons? Some of which go from west to east, and some go from east to west. Jupiter doesn't discriminate. And that's additional evidence that the moon came from the Earth. By the way, the density of the moon is almost exactly the density of the mantle, the outer portion of the Earth, because that's where the material came from. It has very little iron, and therefore it has no magnetic field, a point which I'm going to stress again in a few minutes. Because the iron in the core of the Earth is what gives us a magnetic field. Fascinating. So here's some sizes in our solar system, just to give you an idea. This is the Earth, okay? The second one here, I'll have to read this for you, is Venus, okay? The third one is Mars. The fourth one is Ganymede. That's the biggest satellite. Then Titan, which is a satellite of Saturn. Then the planet Mercury. And then Io. And then the moon. There's our moon. So you can see, compared to the Earth, our moon is huge. Yes?
So the moon does not rotate by itself? In other words...
No, we're locked together. We're locked together.
That's why the moon is not rotating around the Earth? In other words, those two are...
The moon and the Earth are rotating about the center of mass of that barbell. And that center of mass is what's rotating, is revolving around the sun.
So would that explain why sometimes in midday you can see the sun, the moon?
No, that goes back to because it rises about 52 minutes later each day.
Because sometimes it seems like the moon is up at like 1 in the afternoon.
It is, always. Every month it happens.
And so,
Yeah.
all right.
Depends on the phase. Depends on the phase of the moon. 52.7 minutes later each day. So the Earth-Moon system is the only double planet in the solar system. Now, let's talk about the economic incentive for going to the moon. And this is a picture of a remotely controlled vehicle that is searching for oxygen and other lunar volatile materials on the surface of the moon, which is called the regolith. there are basically 4 reasons that I could identify for going to the moon as economic incentives. Entertainment. Boy, wouldn't it be great if Steven Spielberg could take a movie set to the moon. Minerals, like titanium, which exists in significant quantities, not great, but significant quantities on the surface of the moon. It would cost so much to bring it back to the Earth that it wouldn't be worth it, okay? It just wouldn't be worth it, because you've still got to use a lot of fuel to get it off the moon and then to slow that thing down when it got close to the Earth. And you have to set up a whole mining operation and so forth. As a launching platform to other planets, asteroids, etc., again, using the International Space Station would be more efficient and economical because you don't have to use as much fuel. It's fuel. To put 1 kilogram in orbit costs about $50,000. Remember I said a kilogram is 2.2 pounds. 50,000, so about $25,000 a pound. It's expensive. It's your money and ours, folks. Thank NASA. And finally, helium-3 may be the only economic incentive for going to the moon. If we can build a fusion reactor, and people and companies are working furiously on this, if we can build a fusion reactor instead of a fission reactor, this could make a trip to the moon and an excursion to mine the moon's surface economically feasible. Helium-3 could be used in a reactor, a fusion reactor, to virtually eliminate excess radioactive material and prolong the life of the reactor. It exists in much larger concentrations on the moon than it does on the Earth. The magnetic field of the Earth prevents helium-3 from hitting the surface of the Earth. But the moon's weak magnetic field has allowed the lunar soil to absorb helium-3 for about 3.5 billion years.